Welcome to the Nuclear and Particle Physics Research Facility at Old Dominion University. My name is Gail Dodge and I'm the Dean of the College of Sciences, and I want to show you a little bit about this fabulous facility we have here at ODU. Today we want to show you a little bit about the capabilities of this facility, but first I want to tell you something about the Nuclear Physics Research Group. At ODU we have a lot of faculty who do experimental nuclear physics. Those are the people who prepare experiments for Jefferson Lab, and they do a lot of that work in this room with their students and postdocs, graduate students.
Hi, I'm Professor Larry Weinstein. I'm an experimental nuclear physicist, and that means that I teach courses here at ODU, and I smash atoms at Jefferson Lab. Now, Jefferson Lab is one of the country's best nuclear physics laboratories, and we study the nucleus of the atom there. How do protons and neutrons make up the nucleus? How do quarks and gluons make up the proton and the neutron? The way we study the nucleus is we study it like a 5-year-old. We hit it hard, we see what comes out. Now, of course, to hit it hard, we need a really small hammer, and Jefferson Lab accelerates electrons until they're going at 99 point lots more nines % of the speed of light. So they're going really, really fast. They've got lots of momentum. They've got lots of energy. They hit the nucleus, and so this beam of electrons hits a target. Every now and then, one of the electrons in the beam hits one of the nuclei on the target, bounces off. We detect that electron, and so we know how hard it hit the nucleus. Then we detect the particles that it knocked out. So if an electron hits a proton in the nucleus and knocks it out, we can detect the electron and the proton, figure out what the proton was doing in the nucleus before we hit it. It's kind of like reconstructing a car crash. This car hit that car, they both skidded a certain distance. From the skid marks, we can figure out how fast they were going before the collision and who was at fault. Here, we want to figure out what the proton was doing in the nucleus before the collision. To do that, we have to detect those particles, and to detect something that small, we need really big detectors. Basically, the smaller the thing we're looking at, the bigger the microscope we need. And so what you can see here is a picture of some of the detectors at Jefferson Lab, and this thing is 1,000 tons, so it's pretty big. And here's a close-up of another one, and you can see these are incredibly complicated. They've got hundreds or thousands of detectors and detector channels, and we get to play with these great toys, and we involve a lot of undergraduate and graduate students in our research at Jefferson Lab.
We also have faculty who mainly focus on the theory and doing computational projects and predictions for experiments. Those faculty work together with experimentalists to plan experiments, and we have a lot of very well-renowned faculty of both kinds here at ODU. We have a very large group, one of the largest nuclear physics groups in the country, and our faculty work together to have a very large impact.
Hi, I'm Sebastian Cohen. I'm a professor here at Old Dominion University in the physics department, and my specialty is nuclear and particle experimental physics. So one of the wonderful things of being at ODU is that we are very close to a major national lab called the Jefferson Lab in Newport News. It's just a half-hour drive from here, and so our students get to have it both ways. They have the very individual attention of the faculty here at the university, and at the same time they can also mingle with some of the leading scientists from all over doing research at Jefferson Lab. It's about 500 staff and 1,600 users from every part of the world. So what we have the opportunity to do is we can build our own apparatus for experiments that we then do at Jefferson Lab. So we build something here in our labs, and usually with students, both undergraduate and graduate students involved, and then we take these devices and do measurements at this national lab with 12 GeV electron. So for example, right now we are in the middle of an experiment called BONUS at Jefferson Lab, which takes a total of 12 weeks of beam time experimental balls called B, and detector, which our group also built some part of, the class 12, is where we install our device. But for this particular experiment, we needed to build a dedicated small detector, which we started here on campus. So this detector is basically made of concentric electrodes. This is an example. So this semi-translucent electrode allows us to amplify a signal from particles that are scattered from the electron beam, and then it gets read out. So this thing, you have to imagine this thing inside a larger detector that we then read out and send the signals to our data acquisition computer. So just to give you an example, we had about half dozen undergraduate students and as many graduate students working on various aspects of this particular detector. You can actually see, if you focus over there, how this thing looked in the end when we brought it to Jefferson Lab. We did everything from testing and testing these foils, building them into cylinders, to setting up a gas and high voltage system that we use to run the detector and make sure it works. And we also wrote the software to analyze the results. And we've been taking data since beginning of, since the middle of February of this year. So something we built here at ODU is now going to be the center point for this new experiment.
We have a lot of award-winning faculty in our group, and faculty who are known around the world for their work here.
So, in order to figure out what's inside the nucleus and what the protons and neutrons are doing there, what's inside the protons and neutrons, what the quarks and gluons are doing inside the protons and neutrons, we study subatomic collisions. The electron hit the nucleus, bounced off. We need to detect that electron. It knocked out other subatomic particles. We need to detect them. We need to figure out what they are. Was it an electron? Was it a proton? How fast they were going? How much energy did they have? To do that, we use a lot of different detectors. And so inside that 1,000-ton detector that we looked at, there are scintillators that were also discussed, and there are things called wire chambers. And wire chambers allow us to measure the location of the particle to about 1/10 of a millimeter. How does this help? Well, after the collision, might have a stack of several wire chambers. We measure where the particle was here, and then here, and then here, and that helps us know what the momentum is. So how does a wire chamber work? Well, here's a prototype we built, which only has about 30-some wires. The final ones we built had about 10,000. And the way it works, I have to put this down and use both hands, is a charged particle passes through the gas, knocks out electrons from the atoms in the gas, and then we have a wire in the middle. We have this wire, it's really positively charged, the electrons are drifting toward it, and the electrons start going so fast when they hit the next gas molecule, they knock another electron out. And we had 1 electron, then 2, then 4, then 8, we get a whole avalanche of electrons, hits this wire, we get a signal. So this charged subatomic particle that no one can see or feel zooms through the wire chamber, knocks electrons loose, we collect those electrons on one of the thousands of wires in the wire chamber. And by timing the arrival of those electrons, we can measure where that charged particle passed through the wire chamber to within 1/10 of a millimeter. So what we did, that this was a prototype for, was we built 6 of these wire chambers for Jefferson Lab. But not these. We built wire chambers that were 10 feet across, that had several thousand fine wires. And those wires, if we want to measure the position of the particles that pass through to 1/10 of a millimeter, those wires have to be positioned to 1/10 of a millimeter. And some of those wires are finer than a human hair. So as you can imagine, it took us several years to build these 6 wire chambers with these thousands of wires, and these things that are 10-foot triangles that were then assembled, 6 of these triangles, into a really large pizza in order to detect the charged particles knocked out of these subatomic collisions, so we can figure out what's going on inside the nucleus. So we built those wire chambers in this room here. What's special about this room? It's a clean room. At the top of the room, we've got about 8 blowers with incredibly fine filters. And so they're blowing the air in through the filters that takes all the dust out of the air. And so air is flowing, clean air is flowing down, gets to the bottom of the clean room, flows out. So this is a room with very little dust in the air. And that's really important because when you want to measure particles with wires that are finer than a human hair, any dust on those wires will cause lots of problems. So we built this clean room in order to build those 6 wire chambers for Jefferson Lab in here.
So in this clean room, you can see a number of really interesting things. One is we have this big rust-colored crane inside there. That's because the detectors we're working on are so heavy that we have to pick them up with a crane to move them around and to work with them. So we have a crane inside, and then outside the clean room, we also have a crane in the ceiling. You can see it's blue right there, which holds 3 tons. So we can also pick up detectors outside the clean room, and we can move them as needed over to this outside door. This roll-top door is where we can have a big 18-wheeler truck back in here, and we can actually put a detector on that truck bed by using that huge blue crane up there. So we have a lot of capabilities here to build really, really huge detectors the size of this clean room. And that's what we're specializing in doing, and that's what this room was built to do. So it's pretty interesting when we have those trucks come in here. And of course, when you're trucking a detector up to Jefferson Lab, and it has thousands of wires smaller than a human hair, the chances of those wires not breaking because you go over a pothole, that's what we have to plan for. So we've had a pretty good track record, but this is the kind of thing we worry about.
Hello, I am Professor Charles Hyde, and you can see a picture of me without the mask on the physics department homepage. I also work in experimental nuclear physics, and you see here a poster of a number of projects that we built in this lab, and you see many different people here, many of them undergraduates and graduate students, and I've typically had at least one undergraduate a year doing a senior thesis project with me on either a project like this or a computational project related to nuclear physics. Okay, so I want to talk a little bit about a very important detector technology for high energy particles, which is called plastic scintillators. It's a relatively inexpensive technology, so we can cover very large surfaces, and it has a very fast time response. So this is an example. This is a block of pretty much ordinary plastic. The only thing special is that it's got a couple of dopants. And the basic principle is as a high energy particle goes through any kind of matter, it will ionize some of the molecules along the path, and it will also excite some of the molecules. And those molecules then decay back to their ground state and give up that energy. And the dopant chemicals are tuned so that approximately 2 or 3% of that energy comes out in a flash of blue light. And it actually comes out in 2 stages. It comes out first in a flash of ultraviolet light, and then the second molecule captures that ultraviolet light and turns it into blue light. So I just turned off and turned on the so-called black light or ultraviolet light. So right now the plastic is glowing blue because it's being bombarded by intense ultraviolet light. But for particle detection, we get this flash of blue light directly from the passage of high energy particles. So I want to show you a little more in detail. This is a segment, 5 pieces of plastic scintillator. This was part of a detector array that we built here and installed at an experiment at Jefferson Laboratory. And that's an experiment where I like to describe that we're scattering an electron off of a proton, and so we're exciting the proton, and then it emits a high energy gamma ray, which we use to take a picture of the proton. So what happens here is that we get this flash of light. The flash starts in about 2 nanoseconds, 2 billionths of a second, and lasts for about 10 nanoseconds. So a nanosecond is a billionth of a second. And we like to say that a nanosecond is this, because light travels 1 foot per nanosecond. So we can directly sort of visualize and work with time at the nanosecond scale simply by lengthening or shortening our cables by roughly a foot. Provided, of course, we have electronics which is fast enough to see that. So the light is created in that brilliant short flash. Well, maybe not so brilliant, but we collect maybe 1,000 photons. They bounce around by total internal reflection, kind of the same way that optical fibers work. And then we have a device here called a photomultiplier tube that is kind of like an old-fashioned vacuum tube before the era of transistors. It has extremely high gain and extremely low noise. And the principle of operation was essentially the subject of Albert Einstein's paper on photoelectric effect, which is what he received the Nobel Prize for, not for relativity. That was too speculative. So that flash of light gets turned into a short pulse, and here on the oscilloscope I've got 4 traces, and every now and then you see 1 pulse or 2, or maybe particularly rarely you might see all 4. So those are the 4 different, 4 out of 5 of these separate blocks. The signals are coming in, and I'm using the middle one to trigger the oscilloscope to decide when I should display something. So if you see 1 pulse, it means there were at least 2 blocks that fired. Oh, there was the one that you saw a couple events there where it looks like all 4 of them fired. So a high energy cosmic ray came through the whole stack and made a pulse in each one. But the cosmic rays come in from all sides. They're kind of mostly from above, but so they can go through 1 or 2 or up to all 5 of them. And ouch! Oh, there was one. They come. If you hold out your hands, you get a cosmic ray about once a second. Of course, you don't feel them. That's just part of the natural background radiation that we all experience. It's maybe about half of all the total radiation that we experience from all sources. So, as I said, this was this is a piece of a larger array, which is, I'm showing over here, that we installed at Jefferson Laboratory. There's another large array here. You can see this is mostly meters on the side. That was taken out of Jefferson Lab and refurbished, put back in for a new experiment. So these are the kinds of projects that we work on and our students work on, as well as a lot of work in simulating how this will all fit together in a real experiment.
So this is one of those scintillator detectors that Dr. Hyde talked about. And we've got the plastic scintillator here, and it's sitting on a piece of something that looks like aluminum foil. So when we make a scintillator, we want to keep all that light inside, and so we wrap it with this really reflective coating. And then the light that travels out comes out through these light guides, gets directed to the photomultiplier tube, and then the whole thing gets wrapped in black plastic so that no exterior light can come in. We built about 60 of these for a big detector at Jefferson Lab, and almost all of that work was done by undergraduate students and by our technician, and they did all of the testing and the assembly and the construction, and it was just a great project for undergraduates. One of our undergraduates, named Kitty, actually worked on a wide range of projects. She worked on this project here, building scintillators, and she did a lot of the research that told us how to shield those detectors from magnetic fields. So we rely on her work for operating that detector. She's now a graduate student at a French university doing her PhD work at Jefferson Lab.
We've had a lot of undergraduate students who've gone on to do graduate work at other universities. They've been introduced to other faculty while they've worked here, and they've gotten bit by the bug. They realize how fun it is, and then they go on to do additional work. But even if you're interested in going into industry or some other kind of career, undergraduate research is a fantastic preparation for that. It allows you to work with your hands and think for yourself, and it's really just an excellent complement to the work in the classroom.
And undergraduate research also introduces you to problems that have never been solved before, unlike your classroom problems. So you get to be the first one to find a solution to a particular problem.
We've had a lot of undergraduates do research work with this group over the years. Some of our students actually end up starting in this group in their freshman or sophomore year, and they work with us for 3 or 4 years. They get a tremendous amount of experience, and they have a lot of responsibility usually by the time they finish. So that's not for everyone, but I can only say it's fun to work with electronics and with detectors, and we are well equipped to do that here. So thank you for your interest in this incredible facility. This is a place where undergraduate and graduate students can do really interesting and fun and exciting work in experimental nuclear physics. If that's something that interests you, this is the place for you. ODU is a place where undergraduates can do research. We have a strong program of undergraduate research, and this is just one of the labs where people can get that kind of experience. If you are interested in graduate school in nuclear physics, this is an outstanding facility and with an outstanding group where you can do that kind of work. So thank you for your interest, and please come back when you can see us in person.